Okay, let me solve one eigenvalue problem from scratch. So the matrix is this. It is a nice matrix, symmetric, and okay. So we have to find eigenvalues first. Determinant of A minus lambda I is 1 minus lambda 1, 2, 1, 2 minus lambda 1, and 2, 1, 1 minus lambda. Okay. So that is the 1 minus lambda times this times this, 2 minus lambda, 1 minus lambda, minus 1, and this one minus 1 times this, 1 minus lambda, minus this times this, minus 2, then plus 2 times 1 times 1, 1, minus 2 times 2 minus lambda. Let me double check. 2 minus 1, minus 1, minus 2. This one is 1 times 1. Okay. So, well, let's simplify. Now, the inside, these are simple, but the inside, I can just write this down as lambda minus 2 times lambda minus 1, so it's easier to multiply, minus 1. So let me do the arithmetic up here. So inside I have lambda squared minus 3 lambda plus 2 minus 1. This one is minus 1 minus 2 is minus 1 minus lambda, and this is plus 2 times that is 1 minus 4 plus 2 lambda, right? 1 minus 4 plus 2 lambda, so that's 2 lambda minus 3. So let's expand. I have lambda squared minus 3 lambda, and 2 minus 1 is that 2 minus 1? No, but that is 1. And 3 lambda plus 1 minus lambda 3 plus 3 lambda squared minus lambda. Let me double check. Lambda squared 3 lambda 2 minus 1, that's 1. So this times this, lambda 3 lambda 1, then this time this minus lambda 3 plus 3 lambda squared minus lambda. Okay, so that is this one. And the second one, and so minus minus is plus 1 plus lambda, and this one is plus 4 lambda minus 6. Okay, so minus lambda 3, this one, lambda squared and lambda squared, I have 3 plus 1, that is plus 4 lambda squared, and so this one go away. Lambda minus 3 lambda minus 4 lambda plus 4 lambda, that is 0, so I have just a plus lambda. And the constants, I have 1 plus 1, that's 2, minus 6 minus 1. Okay. Something looks not right. Right. So let me double check, because I think there's something went wrong right here. So let me see. Minus 3 lambda, where's lambda squared? Lambda 3 lambda squared is here, and I have lambda squared minus 1. Oh, okay. Yeah, that's correct. So, yeah, I forgot something. Okay, so this is correct. So I have minus lambda 3 plus 4. You see, when we have minus here, even I get confused. So let's multiply this by negative 1. So we get rid of this negative. I don't like negative. So it's lambda 3 minus, that's why I was just thinking this can't be. Minus lambda plus 4. Okay, that makes sense. Now, this is, I can factor lambda squared here. So I have lambda squared times lambda minus 4. And I can factor minus 1 here, right? So minus lambda minus 4 is 0. So if I factor lambda minus 4, then I will get lambda squared minus 1. So one solution is lambda equals 4, and the other ones are lambda squared minus 1 is 0. So lambda squared is 1, and lambda is plus minus 1. Okay? Now you realize that I was just looking at this, I didn't see this negative here. And I was thinking, if that's lambda 3 plus 4 lambda squared, I cannot factorize this thing. Because I knew I was doing it and I could factorize it, so what happened? So that's what I'm saying. This negative really is sometimes is confusing. But anyway, so let's write them up here somewhere. Let me erase this first line, because I need this space. So I have lambda equals 4, and lambda equals 1, and lambda equals negative 1. And the matrix is this. So I have to solve this. For all three of them, I have to solve this equation. A minus lambda I times vector V, which has 3 components, equals this. So it's a homogeneous system. And I set the determinant of this to 0, which means this matrix, which I will write, should be, cannot be inverted. So it's not inverted, okay? Which means that when I write that matrix, at least one row is redundant. Well, let's write it and I will show you. So let's say lambda 1 is 4. So that A minus lambda I will be this matrix. 1 minus 4 is minus 3, then 1 and then 2 are there. Then 1 is here. 2 minus 4 is minus 2, and 1, and this is 2, 1 minus 3. And this times V1, V2, V3 equals 0, 0, 0. Right? Well, I know that this, I can just throw away one row at least. But let's see, well, I said that this matrix is not invertible, which means at least one of the rows is a linear combination of the other two. Well, this, what linear combination? Let's see. If I multiply this by negative 1 and this one by also negative 1 and add them, right? Or I can add them like this, right? So just add them, add this one and this one. Row 1 plus row 2 is minus 2, minus 1, and 3. You see, minus 2, minus 1, and 3. This is the negative of this. So if I say minus row 1 minus row 2, I will get this. So minus row 1 minus row 2 is the third row. Therefore, the third row is redundant. I don't need the third row. So I can just erase it. So I'm dealing with this. Okay, now this is two equations and three unknowns. I have to reduce it. So use your calculator to reduce this thing, and let me reduce it here. Well, let's see. If I flip this down and put this up here, that would be much easier to. So 1 minus 2, 1 minus 3 minus 2, 1. Minus 2, that's 1 and 2. Let's reduce it. So if I multiply this by 3 and add, so 3 row 1 plus row 2 goes to row 2. Let's see, 3 times this, so I have 1 minus 2, 1. This will be 0. 3 times minus 2 is minus 6, that's minus 5 here. 3 times this, 3 plus 2 is 5. Okay. Let me double check. So 1 times 3, 0. 3 times 2 is 6, minus 6 plus 1 is minus 5. And 3 times 1 is 3 plus 2 is 5. Well, I can get rid of this, that's okay. Okay. So this minus 5 and 5 is what? I can divide by 5. So I will get negative 1 and 1. So divide row 2 by 5. And this is what I get. Let me write down the matrix again. So this divide this by 5, and I have this 1, negative 2, 1, 0, minus 1, 1. Right? Doesn't make a difference if I do that because the other side is 0. So now row number. This one, how can I get rid of this? Well, I can write 2. Look, it's easier to write 2 here. What's the difference? No, nothing. So 2 and 2. So let's add them, or let's say plus 2 or minus, right? So if I add them, minus 1, minus 2, 1. No, this one, I'm adding to the top one. So this is 1, 0, minus 1. And 0, let's just write 1 and 1. Okay, so this is the matrix. And if you reduce it, only else will give you this on your calculator. I think we should do this. Okay, so let me see. And where should I write this? I'm going to erase this thing. So I have V1 minus V3 is 0, and the other one is V2 minus V3 is 0. Well, that's good. So remember, this row will be free because the leading ones are here and here. So I can just choose anything. As I said, just choose something. Let's say V3 is 1. So I will get V1 and V2 equals 1. So for lambda equals 4, so 1, 4 gave me V1, simply 1, 1, 1. Okay. So that is 1, 1, 1. Let me double check here because I probably have the. Yeah, I think that's correct. So 1, 1, 1. Now let's try this one. Lambda equals 1. Where should I write this? So it's right here. So lambda equals 4. And the 1 gave me V1 equals 1, 1. So this, this. Okay. And then let's do this lambda equals 1. So a minus lambda I will be this. 1 minus 1 is 0. 1, 2. 1, 2 minus 1 is 1. 1, 2, 1, 0. But I'm not going to show you this one is a linear combination of these two. You can just do it yourself at home, and v1, v2, v3. So I can just get rid of this, and well, this one I don't have to reduce it. It's not reduced, but I can just live with it. Well, let's see if I write it like this. So let's reduce it. So I can flip this thing. So this is 1, 1, 1, 0, 1, 2 times v1, v2, v3 is 0. If I multiply this by -1 and add -1 and add -1, this will be 0, right? And negative, this will be -1. Correct? 1, 0, 1, 2. Okay. So that gives me v1 minus v3 is 0, and v2 plus 2 v3 is 0. Well, v3, but in the notes I'm not sure if that's minus, yeah, but that is so if v3 is 1, then v1 is also 1, and the v2 is -2. So then the 2 equals 1, that gives me v2 is 1, no, v1 is 1, v2 is -2, and v3 is 1. Okay. And the third one is in -1, so let me erase this. Okay, let's erase this. Okay, so -1 will give me 1 minus -1 is 2 in fact, not 0. And 2 here, 1 here, 2 here, 1, and 2 minus -1, that's 3. 2, 1, 2. Well, you can say this one is exactly this one. So in this case, I'm lucky. So this one goes, and I have v1, v2, v3, 0, 0, 0. So I did the RREF on this, so let me see if I still have it, and RREF gave me something. So the RREF, this gave me this interesting matrix. 1, 0, 1 here, 0, 1, 0 times v1, v2, v3 equals 0. But this kind of equation, you might have seen this before when we did systems of equations, but you might not remember how to do this. It's even simpler than the other ones, but a little confusing. So that's the system. Now let me write equations. Let me write the two equations. And so from the first one, I have v1 minus v3 is 0. The second one is giving me v2 is 0. Okay. Well, since these two are leading ones, then this should be free variable. So if I take v3 to be 1, say, that doesn't affect this one. v2 is 0, I can't do anything, that is 0. But if I take v3 to be 1, at least it gives me v1 to be 1. Okay? So this So that was this one. So the third one, when lambda 3 is -1, V3 is, interesting, that is 1, 0, 1, 0. Okay, I hope you understood the procedure. Now, if we have a matrix which is like 4 by 4, 5 by 5, whatever, don't do this. Unless you have absolutely nothing in hand. Like you're lost in some island somewhere and you just have some pieces of paper to write, then you have to do it if you have to solve anything like this. But you can use even your calculator can do that. So, anyway. Well, we saw two things here. Well, one of them, which I mentioned, I guess, last time, that this matrix is symmetric. A transpose is A. Just look. That is A is symmetric. So we saw two things. Lambdas are real. Well, because we are dealing with complex numbers, we can say it is a complex number with 0 imaginary. Okay. Complex number with 0 imaginary part. So that's one thing which I will show you why this happens. Any symmetric matrix has this property. In fact, if I have a complex, because well, in practice, I mean the problem that I will give you, you see in your book, you don't see any complex entries here. But if I have a complex, entries, then that's something else. And transpose is defined differently for complex matrices with complex entries. Anyway, so this is one thing that if this is symmetric, then this happens. Second thing, let's look at the three eigenvectors. Now I claim that they are orthogonal. I claim that V1 is orthogonal to V2, V1 is orthogonal to V3, and V2 is orthogonal to V3. Let's check. This one times this one, 1, 1, 1, orthogonal means dot product is 0, minus 2, 1. This is 1 minus 2 plus 1, 0. Yeah, this one is correct. The second one is V1, V3, so 1, 1, 1 times 1, 0, 1. 1 plus 0 plus 1 is not 0. What happened? So maybe I made a mistake. Did I? Did I make a mistake here? No, I can't remember. Let me double check and see what I have here. That was correct, but this one was not correct. Something went wrong. So let's do it again. So that was lambda 1 was 4. What did I get? So I had the 1 minus 4, that's minus 3. That was minus 3. V1 plus V2 plus 2 V3 is 0. And the second row was V1 and minus 4 minus 2 V2 plus V3. Let's see. Let me see. Minus 3, 1, 2, 1, minus 2, and 1. Minus 3, 1, 2, and this is this. So I might have made a mistake. So let's see. If I choose one of them to be if I choose, I said I found this one to be 1. Or no, I chose this one to be 1. Well, let's not reduce it and just find it. So let's see. Let's see what mistake I made, because I'm sure that this happens. And I can prove that it happens, so let's try this. And you see the mistakes that you might make. So if I set this, I will get this minus 3v1 plus v2 is that's minus 2, say, and this one will be v1 minus 2v2 is negative 1. Or if I want to put this and add, but by 2 and add, I will get rid of v2. So that is minus 2, that's 6 v1 plus 2 v2 is minus 6, and I have v1 minus 2 v2 is minus 1. Then we can stick somewhere. So that is minus 5. V1 is minus 7. I don't think this is correct. There's something is I'm making some big mistakes somewhere. So I can't remember. Well, let me double check and see what. No, that's correct. That is 111. That was 111. Sorry. So what is the mistake? Is over there? That one. Yes. That was a mistake. Yeah, this is correct. What we did was correct. This is wrong. And let's go back to this one. The reduced one was this 0, 1, 0. And I don't know why. So it is V1 plus V3. I'm not sure if I wrote minus V3. This is V1 and then V2 is 0. This one is 0. If I say V1 is V3 is 1, then V1 will be negative 1. Wow. So this is a mistake. Okay. G. Now it's good to check that. If you have symmetric matrix, then check and see if they are orthogonal. And that will, it's like checking that they are correct. Well, I'm not saying correct, it's like a good check. So this dot, that one, 1, 1, 1, dot this one, minus 1, 0, 1, is minus 1 plus 0 plus 1, which is 0. So this one is also correct, correct. And this time this, let's try that one. We can see that it is correct. So that's 1 minus 2, 1 times minus 1, 0, 1. And that is minus 1 plus 0 plus 1, 0. Check, check, check. So, this is, that's done. They are orthogonal. Now, what is special if this matrix is orthogonal? Well, I mean, these are orthogonal. So if I put these in, so let's make a V matrix. This is matrix now. So a V matrix, and let's put this as columns. First, let's make them unit. So unit vector, this will be 1 over 1, 1, 1, that's square root of 3, 1 over square root of 3, and 1 over square root of 3. That is this one made the unit. That one will be 1 over 1. 1 plus 4, that is 6, right? Square root of 1 plus 4 plus 1, that is 6. Square root of 6 minus 2 over square root of 6, and 1 over square root of 6. And the other one will be minus 1 over square root of 2, 0, 1 over square root of 2. Now, if you use well, if I used, say, Mathematica, for example, it would give me this. I mean, it gives you exact solutions. Well, it can give you exact solutions if you ask for. And that is exact, and most often they give you unit vectors. They won't give you these vectors, they give you unit vectors. This is also V1, remember? VI's are not unique. They are unique up to something. In fact, in this case, they are unique up to just a non-zero multiple. In fact, it's a direction, it's like a vector space, some vector subspace. Anyway, I don't want to get into that too much. Now, there's something special here. If I multiply this by V transpose, or multiply this V transpose by V, what happens? This goes here. Well, I'm not going to write it, but you can see that this is the transpose of this. Let me just write the transpose. So the transpose is this. Then 1 over square root of 6. And 1 over square root of 6. And this one is minus 1 over square root of 2. 0, 1 over square root of 2. And the other one is like that one. So basically I have something like this. So if I put them together, I have this. The V transpose will be V1 as you can see that. Then V2 this way. Or let's say this is V transpose. And V3 transpose. And it is multiplied by V1, V2, and V3. Right? Okay? So it's like this. When I multiply V transpose V, it gives me this. Let me erase this. These extra terms here. We can just make this. So V transpose V. So this time this is first one here. This time this, what do we get? That is a unit vector. V1 transpose times V1, that is the unit, the length or the magnitude squared. So that is 1. This is perpendicular to this. This times this is 0. This time this is also 0. This time this is 0. This time this is 1. This time this is 0, and the third row is like this. Okay, so a symmetric matrix gave me 3 eigenvectors. Then I put those eigenvectors as columns of a matrix. Then this happens. V transpose V will be I. So if I multiply by V inverse, then this is V inverse. Epsilon. So V inverse. Isn't that nice to have V inverse equal to V transpose? Remember, finding V inverse is not easy. That's something. So if A is symmetric, then V, which is V1, V2, Vn, say, satisfies V inverse equals V transpose if V's are normalized. If V's, the I's are normalized. That's what we call normalized, which means, so this is like an orthonormal matrix. That's called an orthonormal matrix. The columns are normalized, say, and they're orthogonal to each other. Normalized means that they have length 1, and they are orthogonal to each other. Okay, so now I will prove both of them here. So let's try the first one. And let me hope that I don't get confused here. It's me. So fact 1, if A and by N is symmetric, its eigen values are real imaginary parts. That's the beginning. Okay, now how can we prove that the matrix is, complex number doesn't have imaginary part? It means that that B is 0. So how can I prove that A plus BI is 0? There's an interesting way to do this. There's a trick. If this equals A minus BI, then A is equal to A. In fact, this is the same. Then B should be minus B, and this gives me 2B is 0, and this gives me B is 0. So a real number has this property that its conjugate equals itself. That gives me Z is real, right? So that's the trick I'm going to use. Another thing is, which I did not discuss, is the magnitude of a complex vector. Complex vector. Okay? Magnitude of a complex vector. So first of all, I didn't discuss magnitude of a complex number. So magnitude or length of a complex number So if I have Z, A plus BI, we can represent this as a vector like this. It's like a vector in fact. And this is A, and this is B. It's like point AB in XY plane. This is the real axis, and this is imaginary axis. And we need this. This is magnitude of Z. What is magnitude of Z? It is, in fact, magnitude of Z is nothing but A squared plus B squared. And remember, A squared plus B squared, I think the last time I showed that this is in fact Z bar. Or the other way, Z bar, Z. No difference. So if you multiply this by A minus BI multiplied, you will get A squared minus B squared I squared. I squared is -1, so that's A squared plus B squared. So Z bar is in fact A squared plus B squared. Okay, so now a magnitude of a complex vector is this. But a complex vector comes, so a complex vector, say, is like this. So I have Z1, Z2, Zn. Say. So the magnitude of this complex vector, remember magnitude of a simple vector was the V transpose times V, or V dot V square root. It's the same thing, except if I transpose this thing, I also do this. So this is in fact square root of V bar times V. V bar times V. So it is something like this. Z1 bar, Z2 bar, Zn bar times Z1, Z2, Zn. And remember, Z1 is magnitude of Z1. So this will result in square root of magnitude of Z1 squared up to magnitude of Zn squared. Okay? So that is in fact the magnitude of each one of them squared. It's like magnitude of a real vector. Remember, magnitude of real vector A, B, C, whatever, A1, A2, blah, blah. That was A1 squared, A2 squared, A3 squared, and so on. Now here is like Z1 squared, but Z1 squared is a complex number. So it is the length of Z1 squared. Okay, so these two are I'm going to use them here. So first of all, if A, V is lambda V, if I have two complex numbers multiplied and I put that bar, I convert them to the conjugate, so the conjugates are also same. So that's what I'm saying. So if I have Z1, Z2 equals A1, A2, then the bars are also the same. So if I apply A, and remember A is symmetric and is real, has real entries, real symmetry. Then A bar, V bar, lambda bar, V bar. But A is A, right? So that is in fact A. Now this tells me something even interesting though. So this tells me that if V is the corresponding eigenvector, corresponds to lambda, then V bar corresponds to lambda bar. So if lambda gives me V, lambda bar gives me V bar. Okay, so that's also something that comes out of this in this situation. In this situation, in fact, that's for any matrix which is real entry. So that's not something we saw that. Another example. No idea. So I will give you examples of complex numbers. So this is I have this. Now I transpose this. Remember when I transpose, I flip, this one flips. This one is just a constant. So it flips, so I have V bar transpose A transpose, and on this side it doesn't change too much. So that's just V bar transpose. Okay. There's V bar transpose. Now I multiply from the right by V. So I have V transpose A and AT are the same, and I multiply it by just V, just V. And on this side I have lambda bar and V bar transpose V. Now this is in fact magnitude of V. Remember, magnitude was Z bar Z. No, it was V bar V. V bar transpose V. Did I make a mistake in writing? So magnitude of V, remember that was square root of V bar transpose V. Right, so where is this square? This one from here is lambda V. So I have V transpose lambda V equals lambda bar V squared. But this lambda is just a constant, so it comes to the left. Transpose V equals lambda bar V squared. And this is again like magnitude of V squared. So that's what I get. Lambda V squared is lambda bar V squared. Now if V doesn't have if the magnitude of V is not zero, which I didn't assume here, but we should assume that the magnitude of V is not zero. We are not looking for zero eigenvectors. So this is not zero. So this implies that lambda and lambda bar are equal. And this implies that lambda is real. And you saw the crucial step was this, from here to here. That was the crucial step. That A is symmetric. Otherwise, I couldn't prove it. Because A is symmetric, that A transpose equals A. And then A times V gives me lambda V and blah, 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 the rest. So that was the crucial step. The rest of them applies to any matrix, n by n matrix. But this really let me prove this fact. Okay, now the other one I will prove when I do something else. So let me, in this time that I have got 3 minutes, so let me just give you an example where we have complex example. Find eigen values and eigenvectors. So A is, let's just write a 2 by 2, which is not symmetric. 2 minus 3, 1 minus, say, 5. So determinant of A minus lambda I is 0, that is determinant, that is 2 minus lambda minus 3, 1 minus 5 minus lambda is 0. So I have 2 minus lambda times minus 5 minus lambda minus plus 3, right, is 0. And so this is in fact lambda minus 2 times lambda plus 5. Negative negative of this, that's lambda squared minus plus in fact plus 3 lambda minus 10 plus 3 is 0. So, oh gee, this doesn't give me a complex. Well, let me see, what can I do? Let's make this into lambda minus 2. So I need something which is positive here, not negative. So maybe if I change this to plus 5, yeah, plus 5. So let's change this to plus 5, plus 5, plus 5. So that's lambda minus 5. And I will get plus 10 plus 3. Yeah, so that didn't have complex. So that, look at this one, I'm sure that has complex. 3 lambda plus 13 is 0. So lambda is minus 3 plus minus 9 minus, well, 4 times 13. 52. So divide by 2. So minus, so that's minus 3, and this is minus for the 3 in fact, right? So this is not a nice problem. So, so lambda is minus 3 over 2 plus square root of 43 over 2 r plus minus. Let me double check, and 5 minus lambda, so that's lambda minus oh gee, minus 2, oh, I forgot to change this thing. So that's minus, in fact, minus 7. it's minus 7 lambda. So this is totally wrong. Let me correct that. I didn't. So that is lambda is 7 plus minus 49 minus 52. This is much better. Over 2. So 49 minus 52, that is 3. So I have lambda is 7 over 2 plus minus square root of 3 over 2i. This makes so yeah, that is much better. So I have this thing for lambdas, and let's find eigenvectors quickly. And I know from what the discussion was that the eigenvectors are conjugates. So an eigenvalues, you can see they're conjugates. So if I find it for one of them, I have the other one. So lambda of 1 is 7 over 2 plus square root of 3 over 2i. So, and remember, when you have 2 by 2, I said just ignore the second row because this is redundant. So I have 2 minus 7 over 2 plus square root of 3 over 2i times v1 minus 3 v2 is 0. If I let v1 be 1, and this is 4 minus 7, that is minus 3, so this is minus 3 over 2 plus, or minus in fact, minus square root of 3 over 2i. So that gives me, if v1 is 1, gives me v2 is, and this guy here divided by 3, so I have minus 1/2 minus square root of 3 over 6i. Okay, so let me quickly write. So lambda 1 was 7 over 2 plus square root of 3 over 2i, and that gave me v1 as a vector. I set v1 to be 1, and v2 is minus 1/2 minus square root of 3 over 2i. So if I separate this thing, I have 1 minus 1/2 plus, what is also minus, because that's minus square root of, that is 0, and the square root of 3 over 6, over 6, the whole thing times I. Okay, so that is for this eigenvalue, and remember the other one is the conjugate of this. So the conjugate of this will be plus here. Okay, so one eigenvalue is this with the minus here, plus 1. And those are the eigenvalues and eigenvectors. So there's lambda 1 and 2, and 2. So the 2 is there. Yeah. Okay, so that was, I gave you 2 examples and proved that a symmetric matrix has real eigenvalues. So